Good evening, everyone. My name is Mark Harvey. I'm a machine learning specialist with Xilinx. And what I'm going to do this evening, together with my colleague John Corey, John is kindly volunteered to man the question and answer panel. So please feel free to type your questions in as we go along. I'm sure John will have all the answers. So what I'm going to do in this next 30 minutes is just lead you through the Xilinx solutions for deployment of convolutional neural networks and show you how Xilinx can enable you in realizing products in which the convolutional neural networks generally have to run in real time. And by real time, obviously what I'm talking about here is high throughput with the lowest possible latency, okay? So I'm going to give you a very quick introduction to the Vitis and Vitis AI tools. I'll dive a little bit deeper down into the design flow. John Ainsley's already covered a little bit of what it means to take a trained model and bring it into a hardware engine, but I'll show you a little bit how we do it in the context of the Xilinx tools. I'll talk about what we deploy on, which targets we have, and then I'll give you some information about how you can actually get started with the Xilinx Vitis and Vitis AI tools, show you some resources that are available to you, and I'll just close out with mentioning that, you know, the focus is mainly on convolutional neural networks in this presentation, but we do have solutions for other forms of machine learning, and I'll just mention those briefly right at the very end. Okay, Vitis and Vitis AI. So the Vitis unified software platform is something that Xilinx introduced a short time ago, and the intention here was to produce a software design environment that opened up programmable logic to other kinds of users, maybe not just hardware engineers, but data scientists and software engineers, and give you a more software-oriented approach to hardware design in programmable logic. So let me just put a pointer on here. So right at the very bottom of the stack, we have basically the targets on which we deploy. This can be any kind of FPGA for Vitis, but in the particular case of machine learning, we're particularly interested in deploying on Zinc or on our Alveo accelerator cards, okay? The Xilinx runtime library is a software layer which runs on the host processor. In the case of Zinc, that would be the ARM processor. In the case of the Alveo card, that would be your x86 processor in your server or on your motherboard. And the XRT is mainly responsible for communication with the programmable logic, and it gives you a software interface into the programmable logic. Then the other part of the Vitis core development tool is just the fairly standard compilers and debugging tools and so on that make up part of any programmable logic design, okay? There's nothing in the Vitis core development kit that is machine learning specific, okay? As we move up the stack, we have a number of accelerated libraries. I'll talk about those in a little bit more detail in another slide. Okay, these are just basically a set of libraries which have functions that have been designed by Xilinx, and they are accelerated in the programmable logic, okay? Then we have another series of tools, and this is the ones that interest us today, that are domain specific and usually interface into some kind of third-party tool or external tool and bring those tools into the Vitis flow. Okay, so in the specific case of Vitis AI, we interface into third-party machine learning frameworks and bring in the results of those third-party frameworks and bring it into the Vitis AI toolkit. So let's look a little bit more at that Vitis AI. So Vitis AI is an add-on to Vitis. It consists, again, of several layers. Down at the bottom, we have the DPUs, the Deep Learning Processor Units. These are basically a series of IP cores which act as accelerators and accelerate the execution of neural networks, okay? Kit contains a series of point tools, and I'll cover these later, but I think John's already talked about the optimization, the quantizing, and the compiling that is absolutely necessary for bringing a trained model into a format that can be implemented and deployed on hardware. Then we have obviously some ancillary tools because, for example, you must have a profiler. You want to understand how quickly your network is running, where the bottlenecks and performance are, and so on. And then we have an AI library with higher level optimized functions. We do provide a series of pre-trained models for those that want to have a pre-trained model and all of the software that goes with them. There's many different kinds of pre-trained models, things like here, there's pose detection, there's object detection, face detection, semantic segmentation, and so on. I believe there's about 60 different models now within our model zoo. And then right at the very top are those third-party frameworks, okay? So we interface into TensorFlow. We also interface into Caffe and PyTorch, okay? And we bring the trained models from those machine learning frameworks. We bring them down through our tools, through the compiling and the quantizing, and into a form which will run on the DPUs, okay? That is basically the function of Vitis AI. We do have an extra parsing front end that we are now supporting in the latest release of Vitis AI. That's the Apache TVM front end. It's not strictly speaking a machine learning framework in the sense that TensorFlow or Caffe or PyTorch are, because TVM does not allow you to do any form of training. But it's basically a parser which can parse many different formats, including the three that you see here. It can parse models in the ONNX format. It can parse models from DarkNet, from MXNet, from TensorFlow Lite. And this has opened up the possibility of bringing many different kinds of models from many different kinds of frameworks into Vitis AI. Okay. So looking at those Vitis libraries, we have a number of different libraries. The ones you see here are just some examples of what is available. In total, we've got more than 500 different functions across all the libraries that we accelerate. Many of these libraries, or I think nearly the vast majority of these libraries, are written in C++. They are all open source. They're all available in source code format to be downloaded from the Xilinx GitHub. Okay? And the idea here is to provide that more software-like experience. Software engineers in general are much more used to having functions available to them within libraries. And I think one of note that we should probably have just, that merits an extra mention amongst all those libraries is the vision and image library, okay? That is a library that's used very often in machine learning. Very often when you're running a neural network, the image or input data must be pre-processed in some way before bringing it into your neural network execution. Now that might be changing the color space, it might be resizing the image, it almost always involves some form of normalization of the pixel values. either by means subtraction or just simply dividing them down such that they move into the range 0 to 1. But all of that is included in the vision and image library. Now, that library gives you the look and feel of OpenCV. So someone developing in software who's used to OpenCV functions, either in Python or C++, will find himself absolutely at home with this vision and image library. He simply has to call the functions from the library in almost exactly the same way as you do within a C or C++ or Python source code software function. And those will be automatically implemented in programmable logic and hence accelerated by the programmable logic, okay? And these libraries really are a key enabler to the whole Vitis philosophy of a software-oriented approach. And that actually just leads me on nicely to this, this example. This is actually a real-world example. It did actually come from one of our customers. And they had a situation where their camera was obviously inputting frames of data. They were doing color space conversion and resizing in OpenCV, but in software. So the pre-processing was done in software. They were running their face detection neural network on our DPU and getting approximately 13 frames per second. Now, the bottleneck in all of this was not the neural network. The bottleneck in all of this was the execution of the pre-processing functions in software. And that is actually quite typical of this kind of pipeline. There's always a lot of, I find with customers, there's always a lot of focus on the performance of the neural network. How many frames per second can you do? What kind of latency do you have? And sometimes we tend to forget that there are other elements in this pipeline, and those elements can be the bottleneck and not the actual neural network itself. So what we did in this particular case was to take these two OpenCV functions and use the vision and image library to translate them into hardware accelerated functions and create a pipeline in hardware as opposed to functions executed on a CPU. And obviously that increased dramatically the throughput. We jumped very easily up to the customer's target of 60 frames per second and reduced dramatically the latency, which in real-time applications is a very, very important metric, and one that you really need to focus on. It's not all just about the throughput. You must be concentrating, especially in real-time vision applications, concentrating on latency, okay? And you'll get the lowest latency by having as many functions as possible in hardware, okay? And having programmable logic offers the advantage of moving functions in and out, if you want, of programmable logic and experimenting and finding where you can get those gains both in throughput and reductions in latency. Okay. So let's, now we've seen what the value is of implementing these neural networks in programmable logic. Let's take a quick look at the actual Vitis AI flow itself. Now, it kind of follows, if you see this, it kind of follows the diagram that we got earlier from John Ainsley. What we have at the beginning is the training and evaluation phase, which is done in one of those external and third-party machine learning frameworks. So TensorFlow, PyTorch, Caffe, MXNet, DarkNet, whichever one you're using. And you will have your data set and you will have all of your training and evaluation code, almost certainly in some form of Python scripting. And you will work inside that machine learning framework, usually in an iterative manner, going back and forward, changing your network, changing your pre and post processing and such. until you've got a trained model. Okay. Now, the trained model that comes out of the machine learning framework will be almost certainly in the floating point, usually 32-bit floating point. Now, that is not an ideal format for execution in hardware, as John has already explained. What we really want to do is get that down to some kind of fixed number of bits, and we do that by following this chain here. Now, the first step that we can run is an optional step, and that's the optimization, or as John was calling it, the pruning step. And the pruning step exploits the redundancies that are present in many networks, and will reduce by zeroing out the weights, it will reduce the number of mathematical operations that are necessary to execute the network. Reducing those number of operations obviously will increase the throughput and reduce the latency. Okay, so we go from a full floating point model through the optimizer, and the pruned model has, as you can see here, some nodes that are missing, some connections that are missing, but it is still floating point. All right. We then take that floating point model and we quantize it. Now, quantizing and compiling are mandatory steps. So we quantize, we take that quantized model. It generally is 8-bit, but we, as John mentioned, you can have other bit sizes, other bit widths. We, as you will see later, we do have a 4-bit DPU now. And our research organizations work with binary neural networks, so 1-bit neural networks. So, however, you're going down to a quantized model with a certain number of bits. Then that is compiled, and then the compiler basically breaks down the quantized model. It breaks down into a set of instructions and data, okay? And those instructions and data end up in a compiled model file. Now, in the case of our Alveo cards, that's got an .x model extension. In the case of our Xilinx devices, that's an ELF file, a .elf file, okay? But that doesn't really matter too much. It's just a file of a certain format that contains the instructions and data for executing the neural network that we had all the way back here in the beginning in our Python scripts. Once we have that, we move to the hardware and software integration phase. Now, I'll cover the details later, but basically what comes out of that is something that will run on Xilinx or something that will run on Alveo. Now, in the case of Xilinx, your hardware and software integration phase is kind of mandatory. In the case of Alveo, if you are implementing our DPU, we provide the DPU as what is known as an overlay. Basically, it's, let's call it a fixed function that will you've programmed or you download onto the Alveo card. So there is no hardware design required. And so there is no hardware and software integration phase. It is just simply download to here of the DPU, then download the X model. That's it. So there's no hardware design phase. That's quite, it's intentional, and it's basically because we have two kinds of persona who use machine learning. We have the chip down designer, maybe the embedded designer, who's trying to fit as many functions as he possibly can within the Xilinx device. Machine learning is only just one of those functions. Then we have a kind of a data scientist persona who's much more interested in ease of use. He doesn't want to get involved in hardware design. He might not know how to do hardware design. So basically, he just wants to download models and run those models. Okay. So as I was talking about the optimizer, so here's a little bit more detail and the effects it can have on both model size and model performance. you can see that the blue bars here are the number of operations required by the network. In this particular case, we're looking at a single shot detector object detection network with a VGG backbone. And that in its initial state requires 117 gigaops to execute and to process one frame of data. Okay. The gray bars are indicating the metric that's often used for this kind of object detection, which is mean average precision. Okay, MAP, you can see here is mean average precision. It's a metric often used in object detection. And you can see at the very start, we've got 117 gigaops necessary for processing one frame and a mean average precision of 61.5. And as we go through the pruning process, and it is an iterative process, you generally do not try to prune by, say, 70, 80% in one step. You would prune by approximately 10% per step and run 7-8 steps to get to that 70-80% of pruning. And you can see as we move through the pruning operations here that the number of operations required is dropping rapidly, 57, 37, 27, all the way down. After 12 iterations, we're down to 11.6. So that's a 10x factor of reduction in the network. Okay, we've reduced the network operations by a factor of 10. But the mean average precision has pretty much remained constant all the way through. You can see compared to where we started, we're at 61.5, and where we end, we're at 60.4. Now, you can obviously stop at any one of these steps. You don't have to go and continue and continue. You can do 1 iteration, 2, 10, whatever you like. And you can see even in some cases that the mean average precision has actually increased. Okay, so we've reduced the network, but it's increased. Now, that is mainly because after each pruning step, and after we zero out those weights, we do a fine tuning, which is effectively a retraining of the network. Okay, so at every one of these steps, we prune through our proprietary algorithms, which reduce the weights, and then we retrain to bring the metric, which might be accuracy, or in this case, mean average precision, to bring that metric back up to where it was. Okay, and then sometimes, we could even get slightly better results with a network that's almost half as big as the original. And you can see the impact this has on performance. At the end of the day, pruning is really there to bring up performance. We're at 18 frames per second to start off with. Now, at the very end, we're at 103 frames per second. Okay? So a huge impact on the performance. Now, just be aware that some neural networks have a lot of redundancy, some have less. So pruning will have either a much larger impact or a smaller impact according to the type of network that you're running. But this kind of 10x is fairly typical of these networks. If you've got something like a dense net, you might not get to a 10x factor of reduction. Okay. Then the two mandatory steps, the pruning is always an optional step. The two mandatory steps are the quantizing and the compiling. The quantizing uses a calibration data set to establish the dynamic range. Now, the calibration data set is not something special that you have to invent. It is nothing other than some random samples from your original training set. Okay, so if I've got to say a 50,000 sample images for my training set, I can take roughly 1,000 random samples from that set and use it for the calibration data set during the quantizing. Okay? The quantizing has itself an optional step if you wish. You can do a fine tuning on the quantizing, and that again involves a form of retraining. Generally, the accuracy at the end will be sufficient. Okay, You should expect to see some slight drop in accuracy after you've quantized it. If you think about it, we're taking 32-bit floating point numbers and squeezing them all the way down into perhaps 8 bits, so into just 256 buckets. That you cannot do that, take that dynamic range and squeeze it down like that without having some form of negative impact on things like accuracy. If I take an example here, ResNet 50, the top one floating point was 74.76 accuracy. On the 8-bit quantized, we've got 73.74. So we've lost about 1% accuracy when we move from floating point to quantized. I could possibly fine tune that and recover it, but generally for most applications, losing 1% is usually acceptable. Once we come out of the quantizing, we move into the compiling, and this is where we do a lot of optimization on the network. And then we generate those instructions. So basically you get out a binary file, which, as I said, is either going to be an X model file for Alveo or an ELF file for the Zinc. So let's have a little bit more look at what it means to run all of those things together. So this is the Vitis AI flow that I've been talking about. You can see that we have the optimizer, the quantizer, the compiler, and then our compiled model. In parallel to that, you can, or you will probably need to build a hardware platform. And this is something that's a little bit more particular for the edge solutions, so based on Zinc. And here you're basically working within Vitis, and you're building your hardware platform. It's obviously going to have to include some DPUs. It's going to include either C or C++ or RTL source files. As you know, we're showing C and C++ here, but we have not forgotten about RTL designers. They are still, enabled to work exactly in VHDL or Verilog if they wish so. And then you may have functions from those libraries that I talked about earlier. Those are compiled down and linked down into the hardware platform, okay? And you obviously have to build your software platform. That'll include your application code, which needs to be compiled, okay? It will include the Vitis AI runtime. That's absolutely necessary. It may or may not include some functions from our Vitis AI library. And then your compiled model file goes into the file system. And when the DPU runs, it picks up that model file and executes the network, okay? So what are we deploying on exactly, and why did we make certain choices? So for Edge, Edge is, the new fancy marketing term for what we've always been calling it embedded. For Edge kind of applications, we've focused on the Zinc family. The main reasons for that obviously are, number one, that it has these built-in ARM processors, either the quad Cortex A53s in the MPSoC or the dual Cortex A9s in the Zinc 7000 families. And some of the devices, the EV devices, also include video codecs. That can often be extremely useful in machine learning, especially if you're streaming video in and out, and you can compress it and decompress it on chip. That becomes extremely important. They do include a GPU and a DisplayPort output for perhaps outputting the results of your machine learning algorithm. Now, say there's a GPU, just be aware this is not a general purpose GPU that can be used for implementing machine learning algorithms. That isn't going to work for you, okay? So it's just mainly a GPU for generating displays and outputting that display through the DisplayPort interface. And then obviously we have a series of other interfaces that are built and peripherals that are present on this device. especially things like Gigabit Ethernet, USB for cameras, and MIPI for cameras and other forms of vision sensors. So it's a platform that was absolutely ideal for implementing convolutional neural networks, especially within an embedded vision scenario. For cloud and data center, we have this family of Alveo PCI Express accelerator cards. We support pretty much the entire family. The only one that's still outside of the tools at the moment, because it's very new, is the U25. But all of the mainstream ones, the U50 and 280, which the high bandwidth memory cards. There's the new version of the U50 with the low voltage devices on board, and the more mature U200 and U250 Alveo cards. These are just basically PCI Express cards. They're Gen 3 by 16. And one of the great advantages of these is that no hardware development is necessary. We can provide you with everything that you need to get up and running without doing any hardware development, which really suits the data scientist kind of persona who's going to be using these Alveo cards. So the DPU itself, as I said, it is a soft core. It's AXI-based. It has no strange interfaces. It's just it's purely 100% AXI-based. There is a family of DPUs depending on which kind of target you're going for. So we have DPUs that work on Zinc. We have DPUs that work on the HBM Alveo boards, and DPUs which work on the Alveo boards that have DDR external memories. Obviously, in the case of the Alveo boards, you have a PCI interface as well, and they're highly optimized for throughput, and some of the DPUs are also optimized for the lowest possible latency. They act as co-processors to a main host processor. In the particular, in the case of the Zinc device, that main processor is the ARM. In the case of the Alveo board, that would be your x86 class processor, and they're not, shall I say, they are almost autonomous. They have their own DMA built into them. All that it requires for a processor to do is basically point the DPU to the model file that it needs to use, point it to the input data, and basically start it off. And the DPU will fetch that data, fetch the model file, execute the model file and the data, and write the results back into the memory that it shares with the host processor, and then interrupt the host processor once it's finished. Okay, so it is largely autonomous. Okay. So this is just perhaps repeating a little bit of what I've already mentioned. Okay, so we do have DPUs for all of these families of targets. The U200, 250, which are our DDR-based Alveo boards. There's some other DPUs for the HBM-based boards, and obviously the DPUs for the Zinc. Okay, I won't labor that point too much. One thing that is coming down the pipe, we've actually published a white paper about this. We're still a little bit early to be able to give you access to this in Vitis AI, but we are actively working on bringing to the market a 4-bit DPU. All the other DPUs I've talked about so far are all 8-bit DPUs. So especially in the ADAS and autonomous driving space, we're being asked by our customers to give them the maximum performance possible with the minimum power envelope and at minimum cost. And what we've done is come up with a 4-bit DPU. Naturally, it has half the number of bits, so this basically gives us almost half the number of memory that's required and half the number of compute resources that are required. And those are very often resources which are precious, and when you're you often run out of these quicker than you run out of general logic. And this 4-bit DPU gives you, you can either have half the number of memory, the amount of memory and compute resources, or you can double up almost on your performance with the same number of memory and compute resources. So we just look at some examples here. A semantic segmentation with an FPN network. There is a slight drop in accuracy as we move from 8 bits to 4 bits. The same again for classification. This is just a ResNet 50 on the ImageNet dataset. And then 3D detection for LiDAR applications using point pillars network. So these, as you can see, there is, however, going from 8 bits to 4 bits, there is some slight drop. Now you would expect going from 8 to 4, perhaps, to lose a large amount of accuracy or some other metric that you're using. In reality, what we do is we do a form of quantization-aware training. And that quantization-aware training, rather than just training purely in floating point and then quantizing, we basically, shall we say, I think the best way to describe it is we kind of quantize and train together. And that is what allows us to go down to 4 bits, so losing half our number of bits, but still maintain almost the same level of accuracy. And obviously the advantage it gives us is a dramatic increase in the number of tops that teraops that we can achieve. So on a ZCU102 evaluation board, you can go from the 8-bit version, which has got about 3.7 teraops maximum theoretical performance. You can go up to 7.3, 7.4 teraops of performance with the 4-bit DPU. Okay, so there's a trade-off to be made. Do you want half the resources, or do you want twice the compute power? You can choose. And that'll be coming along quite soon. I believe it's going to be ready before the end of this year. So how do we get started with all of these tools? So Vitis AI itself is actually free. There's no charge for Vitis AI except for the pruning part of it. That does have a license and it does have a cost. I would encourage you to talk to your sales contacts about that. However, the Vitis AI tools without the pruning, you can just simply download them from GitHub. They are provided either to be installed separately, or what we do encourage people to do, especially at the start, is just to use the Dockerized version. So you get a Docker container, and that makes it so much easier just to have everything in there. We put everything in the Docker container, not just our Vitis AI tools. If you're going to be using GPUs, then we will build in CUDA and CUDNN into the Docker. So there's basically nothing that you need to install. You just install Docker and download the Docker image and spin up the container, and you're good to go. Okay, so the link is here, and I encourage you all to go to that link, get downloading, and get yourself started with Vitis AI. We do provide, as I mentioned right at the very start, a series of pre-compiled models, pre-trained models, I think is probably the best way of saying it. Pre-trained using a series of different frameworks, TensorFlow and PyTorch, Caffe and Darknet. When you go to the GitHub link here, this is basically what you will see. You will see up to, this is just a snapshot of the first 15. I believe there's nearly 60 models these days. And you'll see the kind of model we're using. It'll tell you what the framework is. And we also give you benchmarking numbers, okay? So if all you're interested in is just finding out, well, how fast can Xilinx do I don't know, an Inception V1 on ImageNet at 224 by 224 samples? Well, the answer is 1,536 frames per second. Now that is just purely the DPU execution time, okay? It doesn't include pre and post processing, which, as I mentioned earlier, can be, can be a bottleneck if they are done in software. We're just including purely the DPU execution time itself. Unfortunately, I've cut off a column here. We also give latency numbers, not just throughput numbers. Okay, and those performance numbers are given for different platforms and different DPU sizes and different DPU scenarios. And we've got them for the edge boards and for the Alveo boards. Okay, so you can look up any one of our boards, pick a network, and get some idea of what kind of performance you're going to get in your application. Okay. The other features that are available to you to get started are the Vitis AI tutorials. So these are actually written by the Xilinx ML specialists, including myself and my colleague who's doing the question and answers, John. John has contributed to these as well. These are basically tutorials which will take you through the complete flow. Most of them do include the training phase. For example, I just pick one here because it just happens to be mine, the MNIST classification with TensorFlow. So that's basically your kind of hello world of machine learning. And we'll do the classification of those 10 digits with a convolutional neural network. And there's everything provided in the tutorial. You know, your training scripts are in there. Your scripts to run Vitis AI are in there. Some application code to run on the board is there. Generally, these tutorials rely on a platform that we have pre-packaged. We do provide, for our evaluation boards, we do provide SD card images, which include both the hardware and the software platform. And so what you get on the SD card is basically everything you need to be up and running very, very quickly. And all you have to provide at that point is either the ELF file to run and your model and run it on that platform. So this tutorial, for example, will take you through the training, the quantization and the compiling of a simple convolutional neural network trained on the MNIST flow, and then it'll show you how to get that on the board. It'll provide you with Python code for running the application, because your application can either be in Python or C++, and you'll be up and running and doing classification very, very quickly. Okay? So I'd encourage you to take a look at those tutorials. This is just some of them. I believe we've got about 15 different tutorials now available, and more in the works. Then if you feel that you do need training, we do have a 2-day course which shows you and will lead you through Vitis AI. It covers the Vitis AI design flow. Okay, it doesn't cover the principles of machine learning. It will not teach you some of the points that you've seen today from John Ainley. You will not get to trained on things like what is a convolutional layer, what is a dropout layer, what is a batch norm layer. But it will show you how to take the model and get to a design running on the board. Okay, I think there's 16 hours, 16 hours of training, so that's basically split over 2 days, and 5 hands-on labs. Okay, so you'll be pretty much an expert on everything related to Vitis AI by the time you've finished that. So just to conclude, as I said, I've talked a lot about convolutional neural networks because the DPU is basically a convolutional neural network accelerator. But Xilinx is branching out into many other forms of machine learning. We do have a new library as part of those Vitis libraries that I was talking about, and that's the data analytics library that was introduced with Vitis 2020.1, the latest release. And that introduced some other machine learning algorithms. So we have in the data analytics library, we now have decision trees and random forests and other things like k-means clustering and so on. So there's a series of other machine learning algorithms that are not, just CNN. And obviously all of these are as part of a Vitis library. They're available in C, C++ code format, but then get converted into hardware and accelerated in the programmable logic, okay? One other thing that we've been working on and we're very active in is in things like recurrent neural networks, LSTMs, and we're very interested and now very active in NLP, natural language processing. One design that we have put together, it's available as a reference design, is we've taken Baidu's Deep Speech 2 model and implemented on a Xilinx MP SoC board. It's actually the ZCU102 board. We actually have two versions, a software-only version, which runs purely on the ARM processors, and then a two hardware accelerated versions, actually. There's a floating point version and a quantized integer version. And you can get any of those and do real-time conversion of things like speech into text. So the quantized hardware version, the conversion time for converting from audio into text is actually less than the duration of the spoken audio, which is exactly what you need to be able to do this in real time, okay? So we're not just focused on convolutional neural networks for vision, we're expanding out into many other forms of machine learning and offering the possibility of accelerating those machine learning algorithms in programmable logic. And I believe, one last summary. So what I've talked about today, I think should have demonstrated to you that we do provide you with a very easy path into machine learning inference or deployment. We give you all of the tools that you need to come out of the machine learning framework of choice with your floating point train model and compress it either through pruning and quantization and turn it into a form that can be accelerated by an acceleration IP, okay? We provide you also with all of the software stack, the runtimes, the APIs, and the examples and tutorials that you will need to be successful with this. We feel that programmable logic, its real value in machine learning is not just about implementing the machine learning algorithm itself. It's about giving you what we call whole application acceleration. It's all about accelerating everything within your pipeline. Okay? I gave you the example earlier of how we could accelerate color space conversion and resizing. That can be obviously expanded to any form of pre-processing or post-processing. Okay? So really the value of programmable logic is this whole application acceleration, not just the machine learning algorithm acceleration. And the fact that our tools are unified across both edge and cloud makes it very easy to take any machine learning algorithm and take the work that you've done, for example, on, say, a cloud platform, and perhaps produce a portable edge design or a product which is perhaps a reduced form factor, and pull that from an Alveo board onto a Xilinx. And those are very, very different platforms. But the unified tool flow allows you to bring those down and just simply compile them and run them on those two platforms without changing your application code. I think that's a very important point to stress. You do not change your application code because all of the APIs and the runtime remain the same between cloud and edge, okay? And I think with that, I have concluded.